So now we're going to see some eddy currents in action. Here is a copper plate that will have eddy currents in it, and here we have an electromagnet. So we're going to pass a big current through these iron cores, and they become magnetized, and it makes a large magnetic field in this gap. Okay? So this plate will slide through there. The magnet is not on. So you can see the plate has a lot of momentum. It'll sit there and swing for many, many, many cycles. When we turn on the magnet, suddenly it's going to run into a region of concentrated magnetic field. So we should have induction because we have a continuous metal object going through many places where the magnetic flux is changing. It'll induce an eddy current, just like we had here, and according to Lenz's law, that eddy current will create a force that opposes motion. So let's get it swinging and see what happens. And I'm going to turn it on, power supply on. Still nothing because I haven't thrown the switch yet. So now when I throw the switch, it's going to create the magnetic field. And we'll see if it can do anything to the thing. There it is. Stops it dead in its tracks. So you can see it moves freely, and as soon as we have a current, stops it. I can actually feel the eddy currents when I leave the current on and push this through. It's actually hard to get it through there. Nothing can get past. It's so strong. Now, one way we can really further confirm that it's eddy currents is we can use a difference slider. So that was sort of a solid piece of copper, and eddy currents were flowing in it. I can also get one that has these little fins. So the next one I'll put in is this one. So you can see it's all slotted, right? It's been cut. So because it's slotted, the eddy currents can't flow over such a large area. You get much smaller eddy currents in these little areas. And they'll create a much smaller force. So let me just change it out real quick for the other one. All right, let's put on this one. And nothing as fun as watching someone do something like this on the internet. And now we let it go, and it goes just fine. And when I turn on the magnetic field, we'll see if it stops at all. Nothing. Just keeps going. I don't even feel a force. I can't feel anything because the eddy currents set up in this are so much more limited than in the solid slider. Another place you might see this is if you have a magnet anywhere near a highly conductive surface. Okay? So here we have this big copper block. And this is interesting. If you get these large neodymium magnets that have large, strong fields, you can actually feel the eddy currents when you move the magnet around on the block. You feel a resistive force. You can kind of see it if you hold it on the corner and let it fall. It looks like it falls quite a bit slower than it should, right? That's the eddy currents always opposing and damping the motion. To see it more dramatically, we can let the magnet roll. So here I'm going to I'll put a similar size wooden block and show you that this thing is heavy. It rolls pretty fast, so here it goes. Pretty good roll there. And if I replace that with the copper block, let's see what happens here. And slowly makes its way down again because of eddy currents. And just so you don't think that we are tricking you and slowing down the tape, here's a piece of chalk and the magnet at the same time. There goes, oh, there goes my chalk. Okay. So this is a much more complicated case. We can't quite draw it as clearly as for the electromagnet. But when you have the big copper block and this large magnet, or this neodymium magnet like this, it's got field lines all kinds of different ways going into the metal. And it really doesn't matter the exact orientation. You'll end up with eddy currents and opposing forces in lots of different orientations. Sort of one good one that's sort of easy to model is to say we're going to drop the magnet straight down onto the block. In this case, we can actually think a little bit about what's going to happen because we know, say that this is the South Pole and this is the North Pole. Well, in that case, the fields are very complicated, but if we simplify it and say they come out like this, so at the beginning you have a magnetic field going out, It's going to make its way from north to south. So right there you have one like that, and it gets weaker and weaker as it falls onto the copper block. So you could ask yourself, what's some imaginary loop in the copper block going to do that sees this field coming? Well, it's going to make, the current is going to flow in a way that opposes the change, right? So according to induction, here the field pointing down is increasing as this thing falls under gravity. As it moves down, the field down is increasing, so the eddy current wants to make a field that points up. It wants to oppose the increasing down field by making a field up. Field up, right-hand rule, would be one that comes around like that, the way I've drawn this, where this is the front and that's the back. So that's the eddy current. But now we could also think about what is the force. Are we sure it creates a force? Well, that's more complicated. If you think about it, we haven't really solved that force problem yet. I haven't given you that equation. What have we done? We've done the force on a free charge. That's not this. That just makes things go in circles. We've done the force on a straight wire. And that was fine. We've done the force on a current loop, but we said the force was 0, and we just got a torque. Well, that's because we did a uniform field. So the hard part about calculating the forces of a circulating loop, or the force on that, is you only get that force when the field is not uniform. So it's a little bit harder to see, and that's why if you look in sort of your freshman physics book, it usually won't tell you the constant force on a magnetic moment, because it has to be in a gradient and the math gets really complicated. But I'm going to tell you the formula. I'm not really supposed to. It's sort of an agreed on thing, freshman, but I'm going to tell you. So just between us, here's the formula. The force that you get when a magnetic moment experiences a gradient it's the gradient mu dot b, okay? So that is getting into some vector calculus we haven't talked about in detail yet. Let me just give you some idea of what that means. Let's simplify it so that we can actually do the vector calculus. Let's do it in 1D. When we do it in 1D, now this gradient, which basically means this del operator, basically means the derivative in 3 dimensions. Here, now if we're going to do it in 1D, we can just call that d dx, how it changes on some axis. So let's imagine we have a field that has a gradient in one direction, like that. Big B decreasing along the x-axis. So B is big here, B is small there, okay? And now we want to know what force does this field gradient create on a magnetic moment, right? A moment being, you could describe this as a magnetic moment. Any magnet, you know, a current loop has a moment. So let's see. Let's see, this we said is what it looks like for a north pole. So this would be kind of the north. Let's see what would happen if it approached. What we're making here is basically another north pole, right? If it's going around like this, north, south, because we want a repulsive force. So what would happen then if we had the moment this way, mu? That would be like bringing the two north poles together, okay? So let's look at the formula. It's the derivative of mu dot b. So now along this axis, we can actually plot mu dot b and see what we get. All right. So mu is a vector, b is a vector that's changing, but they're opposite directions, so it's going to be a negative number, mu dot b. And as you move this way, b gets smaller. Mu is the same size, but b is smaller, so it's going to be a smaller negative number, smaller negative number, smaller negative number as you go this way. So there's a plot of mu dot b, okay? But the force is the derivative of mu dot b. Well, the slope is positive. So the force on the mu is in positive x. So sure enough, it's a repulsive force, just like it's supposed to be. So this is sort of a general equation that will always give you the force if you're in a field gradient. And it's useful in much more complicated situations, but you can actually see it in one dimension. So since eddy currents depend on the material's resistivity, if we can change the resistivity, we might change the effect. So what we're going to do is take our copper block and freeze it to greatly reduce its resistivity. So here I'm going to put it in this Pyrex dish, and we'll pour liquid nitrogen over it and let it cool off. Let's see. really submerge it and let it go. There you can see it boiling away the liquid nitrogen, because to the liquid nitrogen it's pretty warm. This takes a while, so we'll be back in a minute. So now we've frozen our block, and I can definitely feel the forces are now much bigger. The eddy current resistance is very big. But to really be able to compare, I'm going to try to lift it up and get it out of here and put it back on that wooden block so that we have a ramp again. Get that out of the way. This over here, I don't want to stick to it. Don't want to put my tongue on it, as you can imagine. All right. There we go. Out of the way. And trying to get the exact same angle, pretty much right there. Turn it. All right. All right, and we can see now, feel the forces are much bigger, and now we let it roll. Now it's really slow. Definitely slower than before. Let it go again. And the reason is it's cooler, the resistivity is lower, therefore it has a lower resistance to the eddy current. The eddy currents are bigger currents, so they have bigger forces. It'll barely move this way. So in that direction, it can't even get past the friction.